Hi, everybody. We are here in section 14.3, talking about double integrals and polar coordinates today. So the aim today is to grow our powers in taking double integrals so that we can take integrals of new shapes and make some of the older shapes easier to take integrals of. We're going to be looking at polar coordinates, whenever the functions involved are, say already defined in terms of polar coordinates, or there's some, something sweepy about the function. Something where it's easier to define the function in terms of a radius and an angle. And so what we're doing when we're doing a double integral in polar coordinates is starting off at some ray given to us by some angle, maybe theta equals some initial value A. That gives us a ray emanating from the origin at that angle. And what we're going to do is sweep around to another angle, B, where we end. So when we do this double integral in polar coordinates, the outside integral is going to be from A to B, and our outside differential is going to be d theta. And the cross sections in this context are going to look like, kind of like this, where we are emanating from the origin and sweeping out like, I don't know, a fan. You can go like this. In particular, though, we're going to pay attention to when we've got an outside function and an inside function for like an outer radius and an inner radius. And so, yeah, along that line, emanating from the origin, the cross sections are going to go pop, 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 pop. And we're going to pay attention to where the cross section ends and where it begins. And, that's going to give us something to do. Yeah, there are two functions of our radius in terms of theta. So yeah, the boundaries here might be some function of theta. But yeah, on the inside, generally, we can have some function of r and theta. And yeah, this will be maybe some function of, let's call it g. Yeah, this could be some function of theta. This could be some function of theta. Oh, and already it was labeled G1 and G2. What am I doing? So the outer one, G2, the inner one, G1. Okay, great. Those were already labeled. Cool. We are almost there, except one thing that we've kind of glossed over, and I kind of want to leave some room for right now, is that while we've identified that, d theta and dr are going to be part of our area differential, it is not trivial to assume that, the rectangles that we're used to making in terms of dy dx, something that would look like this, is directly going to translate into this new sweepy motion, where if we were going to make grid lines, now this could be horrible, but if we were going to make grid lines, we'd have lines that are, at like a constant radius, even though those don't really look like, especially those last two, pretty garbage. So yeah, those should be circumferences of circles, concentric circles. And then, the other grid lines would look this way. So as we're doing this, we're cutting things into polar coordinates rather than rectangular coordinates. And the shapes of these things, which I've got one pulled out over here, the shapes of these are not necessarily rectangular. They're, portions of a sector of a circle. And so this area differential, it might not be a one-to-one exchange between dy dx and dr d theta. We have to actually think about what would the area of one of these little tiny sections of a sector of a circle actually be like. We would think about this in terms of differentials. So if we were thinking about this distance, I would call this dr, because what that represents is, we've got a radius that could be however long out here, but dr to me signifies a nudge in the radius. And so, the short side of, this side of this thing that's starting to look like a rectangle, especially when you limit things and, make things get a smaller and smaller, finer and finer mesh here. dr is going to be the change in the radius. And then if you think about this length along, the circumference of a circle here, that length would again be approximately a change in the angle times the radius. So the radius times a change in angle. To remind you, going back to the unit circle, if I wanted to figure out, I don't know, how much this distance was along the arc of that circle, all I would need to know is what is the angle here in the middle, theta, and radians are defined exactly this way, such that if we've got an angle of theta here, then we have traversed an arc length of theta out here. So that's the idea that I'm playing off to get this change in angle, theta, but we need to multiply that by r, because r is like the scale factor. We're not on a unit circle here necessarily. The radius should be able to be changed. So the area of this area differential actually ends up looking like r dr d theta. And so we could throw an r in here as well. R dr d theta, which is fun to say if you're a pirate. So that's more of a geometric understanding of what's going on with double integrals and polar coordinates. As a preview of coming attractions, I think in section 14.6, we're going to look at the Jacobian determinant. But you might want to think about the Jacobian as, the multivariable version of, a derivative. It's a derivative between two differentials where we're changing coordinate systems, and we're changing variables even between those coordinate systems. And so, this Jacobian determinant is like a scale factor that you need to multiply by so that areas over here match areas over here. So that's a multivariable similar to back in where calculus 1. Oh my gosh. Yay. Okay, I did look at this earlier, so it's here. You know, back there we looked at differentials where you've got some input nudge x, and there's an output nudge based on that, and the rate at which an input nudge affects an output nudge is the derivative. And so what we're looking at here with the Jacobian is a lot like this, except it's a multivariable context where, in this case, drd theta is playing the role of this differential, and dy dx playing the role of this differential. But yeah, we'll get a little bit more in depth on that soon. I wanted you to see not only a geometric way of understanding that this area differential needs to be r drd theta. There's also this partial derivative way of thinking about this. This is a Jacobian way, where we're taking the determinant of this matrix that's filled with a bunch of partial derivatives, and it works out so that, cosine squared plus sine squared is just 1, and we're left with r drd theta, as being equal to dx dy when we're using these functions to translate from one coordinate system to the other. It's got some chain rule vibes to it too. Okay. All right, so that's probably enough of an introduction. Ooh, we're going to gloss right over the limit definition of a full integral in polar coordinates. There's not too much to pay attention to there, but yeah, I mean, this is important. If you don't, I don't know, this is written out in maybe longer than what I would normally think to do, but because yeah, I mean, it does, this is a nice form used if you are given a function in terms of x and y, and you want to translate it into a function in polar coordinates, because yay, x turns into r cosine theta, y turns into r sine theta, your area differential changes in accordance, and then you've got your boundaries on the double integral. So this is great if you're translating, but if you're already given a function in polar coordinates, writing it this way is overblowing it. This is, if you're given a function in polar coordinates, then you're just going to plug that function in polar coordinates right there. Okay. Here we go. Example number 1. And actually, there are only 4 examples today, and I'm going to keep out on 2 of them to some extent, because, yeah, I think with the 2 that we're going to do in more depth, we'll get a feel for what we need to do, and maybe we'll pick an extra one. Man, I forgot to time myself, but we've been going for about 10 minutes. Okay. First one, find the area of the region R inside this circle and outside the cardioid, the heart shape, over here on the left. So we are finding this blue crescent moon shape. And since we're just finding the area, this is something that we probably did. Well, I guess this would have been calculus 2 when we did stuff with, parametric equations and polar coordinates and that kind of stuff. We probably have already done this kind of a thing. So it's maybe not leveling up for this kind of problem, but being able to phrase this in terms of a double integral is going to allow us to think about a function even hovering above this domain, above this area. So, we've got, kind of an XY plane here, but what a multivariable, a double integral understanding of things is going to allow us to do is to put some function above this and do that. But anyways, that's not part of this problem. We're just finding area. The function that we're going to be working with is just, 1. Anyways, if we want to set up this double integral, we're going to be anticipating doing RD theta for our area differential. And unlike dy dx, where we were able to, change the order, no big deal, Fubini's theorem, this one, we're not going to change the order that much. It's not too frequently that you have the angle described as a function of the radius. That's just not done very much. So we're taking a double integral over this region R. Our function is just going to be 1 because all we're trying to do is find the area of this. So you can imagine, the area of this is equivalent to the volume of a shape where the z component is 1 over the entire thing. So the piece here is finding out these boundaries of integration, and let's pretend that we don't have a picture that tells us all of this already. Here, we'll erase the theta part at least. That's something that we should solve for. We've been given the fact that we've got, those two functions, so that's no big deal. Those are going to, factor in. Those are radii as functions of theta. Those are actually going to go as the boundaries of our first inside integral. So what we're trying to do is find region inside the circle and outside the cardioid. So we're going to be at all of these rays, we're going to be extending from inside function of cardioid and outside function of circle. So inside function of cardioid, outside function of circle. Those are actually going to be the boundaries of our inner integral. To figure out the boundaries of our outer integral, we need to figure out where these two functions intersect. That's the word. And so if we set 3/2 equal to 1 minus the cosine of theta, and then work a little bit of magic here, that would mean that the cosine of theta would be negative 1/2. Okay. And then I just, added cosine to both sides and subtracted 3/2 from both sides to get that. Thinking about where's the cosine of theta equal to negative 1/2, that's going to happen when theta is, plus or minus, 2 over 3 pi, 2/3 pi, 2 pi thirds. That's the way that I normally say things. So we can erase these now. It's just where the x value here is equal to negative 1/2. 2 pi thirds and negative 2 pi thirds. Those are the boundaries on our integral over here. And actually, one of the things you may have noticed is, could we make this even easier by exploiting some of the symmetry that we have? And the answer is Yes, since we have a function that is, symmetric over the entire region, and um, you know, geometrically, the top half here is equal to the bottom half, we could translate this double integral into 2 times the integral from 0 to 2 pi thirds. And we still are working from the same functions here. And then RD theta. Yeah, we could do that. Those integrals would be the same. So let's keep going. At this point, it should be fairly routine. We're going to take the integral of the inside, or the antiderivative, with respect to r, and the function that we have is r. So this is going to become r squared over 2, and we're going to plug in 3/2, and we're going to plug in 1 minus the cosine of theta. So we do this. Yeah, so we plug in 3/2. Woof. 3/2 squared will be 9/4. So we got 9/8. And then minus 1 minus the cosine of theta squared over 2 d theta. Okay. Yeah, we're gonna have to multiply that out. Is there something that I could do here? Well, we can multiply that 2 in. That would be nice. All right. All right. So if we multiply that 2 in, this becomes 9/4. And we just have, well, those 2's cancel out, so we just have the top part. But let's go ahead and multiply that out. We would have 1 minus 2 cosine theta plus cosine squared theta. Cool. And then we still got to write the d theta. And yeah, most of this will be not too bad to integrate. Maybe we do just a little bit more cleanup before we do that. 9/4 minus 1 would be 5/4. We'd have plus 2 cosine theta, and then minus cosine squared theta d theta, and that's an even power of cosine. So we're going to need to use a little bit of strategy from our trig integrals back in Calc 2 to solve this one. I think the strategy is to make that use a half angle theorem, or double angle theorem. Shoot. All right, so let's do this before we take the integral. Five-fourths plus 2 cosine theta, and then 1 plus cosine 2 theta over 2. Yeah, d theta. I'm cheating. I'm looking at a formula. Yes, I don't have that one memorized. But yeah, now we're at the stage where taking the antiderivative should not be too bad. 5/4 theta Antiderivative of cosine would just be plus 2 sine theta. And here we would have you know what? I should have split this up. Yeah, I could have split this up because this is just 1/2. I could have made this into 3/4. I'm gonna do it now. Sorry. Okay, and then that's just 3/4 theta. And then we can focus on having cosine of 2 theta over 2 and taking the antiderivative of that, which is going to be a sine of 2 theta, but we're going to divide by another factor of 2. So it's going to be 1/4 times the times the sine of 2 theta, and 2 pi thirds and 0 there. Cool. We're nearing the end. All we have to do is plug in those two values. Oh, no more d thetas, sorry. So, okay. Okay, so if we're plugging in 2 pi thirds, this becomes pi halves, because yeah, 2 pi thirds times 3/4 is pi halves. And then plus 2 times the sine of 2 pi thirds, which would be the square root of 2 over 2. No, it's not square root, it's square root of 3 over 2. Yeah. And then minus 1/4 times the sine of 2 theta. 2 times this theta would be 4/3 pi, so we'd be down over in this. Now we'd be over here. We'd be at, yeah, minus 2/3 pi. So the sine there would be negative square root of 3 over 2. And that's that one plugged in. And then when we plug in zeros, since these are all sines or just thetas, if we plug in zeros, all of that's going to turn into 0. 0, 0, 0. So this is just what we're left with. And yeah, feel free to add that up. Cool. That's the area. And yes, the new power that we've gained today is that we could change this initial function of 1 into something else more interesting, like we did when we were finding the moments of inertia and all that kind of stuff on a plate. There might be some kind of density function, which, you know, might be the way that you would think about this. Okay, example number 1, beat to death. Let's keep going. Example number 2, we're taking it easy on this one. Just wanted to highlight this because in example 2, we're looking at an annulus shown in figure 6. Oh, goodness. And I didn't copy figure 6 over. What was I thinking? An annulus is just a ring. Let's see. Where are you at, figure 6? There we go. And what's nice about a ring shaped like this is that it's very easily described in polar coordinates because circles are constant functions in polar coordinates. They've got a constant radius. So the reason that we're looking at this one is because it would be easier to determine the moment of inertia using polar coordinates because this thing is more easily described in polar coordinates. So, that's cool. Here we're finding the moment of inertia around the origin. Yay. But yeah, that is a useful thing about what we're learning today, if you're into moments. Example number 3, evaluate this integral. And again, we're going to take this one a little bit easy. Let's think about what we're looking at here. We are evaluating this integral over a region R, where the R is the unit disk centered at the origin. So picturing what we're doing here, I have it oriented this way suggestively. Does this shape look familiar to anyone when we just look down? I mean, we're looking straight down the x-axis right now. Looks like a bell curve, which is the normal distribution, right? If we look at it in 3D, this is what we have. And the integral that we would be taking would be over this region that's described in a circle. A cool thing about this function is that it's, symmetric radially, so that it kind of makes sense to take an integral in polar coordinates, because again, we've got a circle-y type of function going on. This kind of integral is called a Gaussian integral. And these things are important, definitely for computing the normalizing constant for the normal distribution. And apparently it is useful in physics and quantum mechanics too. And, that's cool. On our activity, we're going to look at one of these because while this integral e to the negative x squared is a non-elementary integral, when you treat this as a double integral in polar coordinates, nice things happen, and you're actually able to utilize the fact that we can make a change of variable. I think we're going here. Yeah, we can change the variable such that we get an extra factor of r here, which allows us to do a u substitution that we wouldn't be able to do otherwise. Doing a double integral in polar coordinates actually allows us to solve a Gaussian integral, which is important mathematically in a variety of areas: physics, statistics. The double integral in polar coordinates for this one, since we're on a unit disk centered at the origin, our radius is going from 0 to 1, and our angle is going from 0 to 2 pi. And only thing here is we translate x squared plus y squared into r squared, using this formula from converting between polar coordinates and rectangular coordinates, Pythagorean theorem. And then it works out that you get pi times 1 minus 1 over e. That's not super special, but it will be super cool to look at this. We're going to look at something very similar on the activity and make a conclusion about the normal distribution. So that'll be cool. And the last one for today, at least the last major example in this section of the text, is this one where we have our region is a triangle bounded by y equals x equals 0, and y equals 1. And we're finding the volume of the solid bounded below by this region and above by the surface x squared plus y squared. You may be saying, Dr. Lundholm, we have done this back in section 14.1? And the answer is yes. We can define this as a double integral where we keep the variables of y and x, and it would be no problem. Actually, it would be easier than what we're about to attempt. All we'd have to do is sketch that region, think about cross sections, decide to set it up dy dx, and go through the motions of solving that double integral and getting a third. That's great. Since we're in the section on double integrals and polar coordinates, wouldn't it be interesting to try to set this up in polar coordinates, even though it's not really advantageous to do so? It's going to be gross. We might punt on this part of the way through, but I think we can at least go through setting up the region, at least in terms of polar coordinates. And we can see how far we get. But again, we would need to use more strategies from trig integrals in calculus too, and that's gross. All right, so yeah, we're setting up a double integral. We have a surface. Our surface is z equals x squared plus y squared. So if we wanted to write that surface in polar coordinates, x squared plus y squared is just equal to r squared. So r squared is our function there. Our area differential will be r d theta. And now we need to think about setting up these boundaries. Right now, it's not immediately obvious as to what the boundaries on the radius will be. It is kind of obvious since we're starting off from the line y equals x and going up to the y-axis. You might be able to tell that the angles right now are going to be from, let's use pink. Pi over 4 for that line y equals x, and then pi halves for the y-axis. So that's something that we might be able to tell. But in order to really get a handle on the radius, it would be good for us to make a sketch. Okay, so we've got the line y equals x. We've got the line y equals 0. X equals 0, which is the y-axis, and that we've got the line y equals 1. And that's our triangle. And we are making a radius. What color haven't I used recently? Orange. Okay. We're making a radius that starts at 0 and ends at this line, which is y equals 1. So our radius starts at 0 and ends at y equals 1. Well, how can we describe that in terms of r and theta? Y is equal to r sine theta. So r sine theta needs to equal 1, which means that r is equal to 1 over the sine of theta, or maybe a little bit more simply, cosecant of theta. Okay, so we're integrating from 0 to the cosecant of theta. And we've got our function, and this is how we would go. Yeah, we just go to the next step. Take an antiderivative. We're taking the antiderivative of r cubed, which turns into 1/4 r to the 4th power. And we're plugging in the cosecant of theta and 0. And maybe I want to give myself a little bit more room here. Yep, so we're plugging that in. Why don't we just bring the 1/4 out front? And so we'd have the cosecant of, cosecant 4th power. And that would just be minus 0 to the 4th power. So I'm just going to write the d theta. So this is where the trig integral looks, maybe not too bad, but in order to do this, we've got an even power of cosecant, which means we would need to change this into cosecant squared theta times, oh goodness, so what's the Pythagorean identity that involves cosecant? Cosecant and cotangent, I forget which way they go. I know sine squared plus cosine squared is equal to 1, but 4:30 on a Friday, my brain's leaking. Yeah, I just want to click on, well, this. Let's just bring this up. I'm failing. Okay. So apparently the identity is cosecant squared is equal to 1 plus cotangent squared. And probably you guys were all yelling that at the screen, and I was the only one not knowing. But yeah, we're gonna from here on out, because I guess major idea, once you know that Pythagorean identity, you're gonna be able to use strategies from the trig integrals. You're basically gonna do a u substitution where u is equal to the cotangent of theta, and since the derivative of the cotangent is negative cosecant squared, that makes for a nice u substitution where, just like we looked at today with that Jacobian thing, all the way up here when we were looking at r dr d theta. Boom. This is the updated version. Yeah, we've got this scale factor between one coordinate system and another. Know that we've been doing that same type of thing every time we do a u substitution. So all the way down here, whoops, those are your homework problems. Pause that video on YouTube. Anyways, yeah, every time we're doing a u substitution, we've got one of those scale factors happening, because negative cosecant squared is the scale factor that translates a d theta nudge into a du nudge as an output. That's the derivative. So, okay, we're making connections. That's good. Going back to this, you're solving these separately now because you've multiplied through here. This one just turns into negative cotangent because this is the derivative of this. And then eventually, after doing all those, substitutions of pi halves and pi fourths in, you get 1/3. Probably not worth it to do it that way. This one, definitely easier. maybe it was useful to, I don't know, try a context where defining those boundaries was difficult. Okay. So honestly, we could call it here. I could, yeah, this section is actually rather short. We could look at your homework questions here and here. That would be a good use of time. If you have time, go ahead and take a look at these homework questions. Or I could just pick another one to do as an extra example, but I don't know. Since I've already offered these, probably just need to work on this. Evaluate the double integral by changing it into polar coordinates. Sketching is helpful, sure. Yeah, we can zoom in and think about this one. Yeah, I would encourage you, go ahead and pause and think about, can you sketch this region given to us by these boundaries of integration, and then think about how to change that into polar coordinates. And yeah, once you're ready, I'll do that real quick. All right, so sketching this region. What this says is our x values go from 0 to the square root of 1 minus y squared. So we got to think about, what does the function x equals the square root of 1 minus y squared look like? Well, we could get a little bit nicer view of this if we squared both sides. And then add y squared to both sides. Wow, that's the unit circle. So this function of y, well, yeah, is part of the unit circle. It's actually just going to be the right half of the unit circle where the x values are positive. So we're looking at the right half of the unit circle for, yeah, the x boundaries. And then we're going from 0 to -1 in terms of our y's. So actually, instead of 0 to -1, yeah, we're only doing the bottom portion of this. Yeah, yeah, cool. So that's our region R, I believe. And if I'm wrong and you guys are right at this, like, pat yourselves on the back. It's great. I think that's our region R, and describing that in terms of polar coordinates should not be too bad. That's just the bottom right-hand corner of the unit circle. So our radius would go from 0 to 1, and you know, you could phrase this a number of ways, but you know, maybe -pi/2 to 0 for our angles. And then if we're just finding the area, oh no, we're not finding the area. We're finding the value of this function. We can translate x squared y squared into r squared to the 3/2, and then we'd have r d theta. And so, yeah, this would become r cubed. Then all of that would become r to the 4th, and then you would, you know, do some definite integration and get your answer in the end. So that one's not too bad. And then this one, you know, I kind of want to leave this one as, you know, a possible bonus point for somebody on our homework day. So yeah, I think I'm gonna call it here. If you guys want to work on this, right now, well, there's still some time left. Go for it. But otherwise, have a great day. I will see you soon.